So in this lecture, we will be discussing about representing a discrete time signal by impulse or impulse responses and what is convolution sum. Now, convolution sum is a very important mathematical description which is also very important with respect to behavioral pattern of systems, by which by this convolution sum we can actually get output if input and impulse response of the system is known. That is why I have clubbed these things together, that representing a discrete time signal, by now we have seen that we can represent a discrete time signal by tabular representation, by functional representation, by sequential representation. Now we will be representing them by impulses or shifted unit impulses and what is convolution sum. And to know convolution sum, it is very important to have the idea of representation of a discrete time signal by shifted unit impulses. So that is why this topic is clubbed together. Now, so let us take one signal, suppose x of n, like we are discussing about discrete time signals, that is why x of n, and let us say that there are say 8 samples in it. It is a finite discrete time signal which has got values like say minus 2.5, minus 1, 1, then let us take these positive values only, it will be better to understand. So 2.5, 1, 3.2, 2, then 4, then 7, then 6, then 9. So 1, 2, 3, 4, 5, 6, 7, 8 values we have covered. So 1, 2, 3, 4, 5, 6, 7 and 8. So in this xn, which is a discrete time signal, we are having 8 values, and let us say that the origin is here. By arrowhead we have already discussed that we define the origin, or 0 is at this point where the arrowhead is. So that is the way of representing a signal, discrete time signal, by sequence. So we can clearly see that these 2 points, this is n is equal to 0. So at this point it is, that means n is equal to minus 1, this is n is equal to minus 2 instant, this is n is equal to 1, this is n is equal to 2, this is n is equal to 3, n is equal to 4 and n is equal to 5. This signal can be also represented by graphical representation, that we have also done. So if we try to represent this graphically, that means at n is equal to 0, the value is say 3.2. Suppose this is 3.2. At n is equal to minus 1, the value is 1. So this is say 1. At n is equal to minus 2, so this is n is equal to minus 2, the value is 2.5. So this is 2.5. So this is 3.2. N is equal to 1, it is, the value is 2. So this value say is 2. At n is equal to 2, the value is 4. So this is 4. At n is equal to 3, suppose this is n is equal to 3, the value is 7, and so on. Let us not take all the values, we have only plotted it till 3, and then we have let us take it also. So at 4 it is equal to 6, and it is say 9 at n is equal to 5. So this is the complete graphical representation of this discrete time signal. Xn is the discrete time signal which has got 8 values, and the arrowhead defines the origin. So, at the origin, that is n is equal to 0, the value is 3.2. At n minus 1 and minus 2, these two are the values 1 and 2.5, and then from n1 to 5 we have got values like 2, then 4, then 7, then 6, and then 9. Now, this is the graphical representation, this is the sequential representation. Now, by unit impulses, I have said initially that representing a discrete time signal by impulse. That means we have defined impulse function. Impulse is a function, del n is a function which is 1 for n is equal to 0, and at n not equal to 0, that means at any other instant that function is 0. That is called impulse function. It is impulse means it is happening at any given instant, at all other instant the value is 0. That means by definition at 0 it has got value of 1, at other than 0 this value is 0. So, now suppose I try to define the signal which is existing at origin, that means it is existing at n is equal to 0. We know that it is existing at n is equal to 0 and the value is 3.2. So, can I define this signal? This is n, this is amplitude. Can I define this signal? Forget about the others, concentrate only in this which is existing at n is equal to 0. So, can I represent this by writing it is 3.2 into delta n? Is it correct? 3.2 is the amplitude of the value multiplied by delta n, and delta n is a function, delta n is a function which is 1 at n is equal to 0 and at other values it is 0. That means what? We are multiplying, it is actually 3.2 multiplied by 1, so it is 3.2 only at n is equal to 0. So, that means we can represent a signal by means of multiplying it with unit impulses, or rather shifted unit impulses, which we will be seeing in the next case. Now, in this case it is existing at n is equal to 0, that is why we are able to represent this by 3.2 multiplied by del n only. Now, if we consider the next signal which is at, say at 1, n is equal to 1, let us consider. So, at n is equal to 1, the signal amplitude is 2, right? Now, by definition del n is 1 at n is equal to 0 and 0 at all other instants. Now, if I write that del n minus 1 is 1 according to this definition, it will be only at n is equal to 1, and other than n is equal to 1 this value is 0. Just think that this n minus 1, because this n minus 1 is considered to be 0. That means n is existing at 1. That means this impulse function is shifted by or delayed by 1 sequence. We have already studied the time shifting property of a signal. That means n minus 1 means it is delayed or moved to the right by 1 instant. That means this is a delayed unit impulse whose value is 1 at n is equal to 1, and other than that it is 0. So, this point we can represent by del n minus 1, and this we can represent as if it is 2 into del of n minus 1, because del of n minus 1, this value is 1 at n is equal to 1. So, this we can represent by 2 into del of n minus 1. And likewise, if you take one negative signal, that means if you say this at n minus 1, this value is also 1. So, this is 1. So, let us take another value, say at n minus 2, at n minus 2 the value is 2.5. Now how can we write this? Can I write this as del n plus 2? We know that del n plus 2 is equal to 1 at n is equal to minus 2. Del n plus 2, del n plus 2 is equal to 1 at n is equal to minus 2, isn't it correct? Because this del n signal is shifted towards left by 2 instants. It is actually advancing the signal. That means we can also, by this definition, if you go, that this n plus 2 is now acting as the origin. That means n is actually existing at minus 2 point. So anything, if a del n signal is advanced by 2 time instants, which is the case here, we can represent that by del n plus 2, that is equal to 1. That means it is the shifted unit impulse towards left. So we can also write this as 2.5 into del n plus 2. That is because this del n plus 2 has got a value of 1 at n is equal to minus 2. So like this we can represent signals, and in total if you add these individual signals, that means we are actually representing the whole signal. That means this particular signal, if you start to write, we can write this as, if you start from very left, the first point is the amplitude is 2.5, it is existing at n minus 2. So it will be multiplied to del n plus 2. So we can write like plus of this amplitude is 1 into it is existing at minus 1, that is why it is del n plus 1. So at this point 0, it is amplitude is 3.2, the function is del n because it is existing at 0. Likewise plus 2 into del of n minus 1 because it is delayed by 1 instant. Next again plus this amplitude is 4 into del n minus 2 plus the next amplitude is 7. So plus 7 into del of n minus 3 plus the next amplitude is 6. So 6 into del n minus 4. At 5 it has got an amplitude of 9. So 9 into del n minus 5. So that is your xn. Xn is equal to this. This is representing a sequence by means of shifted or summation of shifted unit impulses. So together, if we want to represent this in a single mathematical, by a single mathematical expression, we can write it like summation sum k minus infinity to infinity x of k del of n minus k. So this is the representation, mathematical representation of a signal xn by its multiplication of its amplitude and shifted unit impulse. So like this 2.5 is the amplitude at n is equal to minus 2. So this xk is then 2.5 and del n minus k, k value is minus 2. So it's like this. At this point it is 4, that means xk value is at, this is k is equal to 2. So at this point we will take this amplitude is 4. So 4 into del of n minus 2. So this is the representation at second time instant, which is k is equal to 2 and the amplitude is 4. So this part is the amplitude of the signal, and this k represents the position of the signal. position of the unit impulse rather. So, this part xk represents the amplitude of the signal xn, and this k, n minus k is k, represents the position of the unit impulse or the position of the signal, and multiplied together from minus infinity to infinity, this represents the sequence or the signal as a whole. So, this is how we are able to describe a signal mathematically as well as graphically. We can represent a discrete time signal by means of product of its amplitude and shifted unit impulses. Now, let us move to the next topic, that is convolution sum. Convolution sum from the concept of defining a signal by means of summation of shifted unit impulses. From that we will move to convolution sum. Now, what do you know about output and input relation of a system? Now, let us come back to a system or discrete time system. We represent our system by a system equation which says if there is a system like this and its input is xn and output is yn with the system transfer function t, we say that we define the system in this way: output yn is equal to the transfer function of the system and which is applied to the input or over the input. So, input applied to the system works with the input by its transfer function and produces the output. So, convolution sum now, and by now we have discussed that xn can be represented by this expression, which means that it can be represented by summation of shifted unit impulses. So, that also we have discussed. So, and the definition of convolution sum or the importance of convolution sum is we can find the output of a system if the input and the impulse response of the system is known. Now, see, look at this system, the input is obviously known. Now, if the impulse response of the system is known, that means we are able to predict the output from any system. Now, what is an impulse response? Impulse response is very simple. We have also told this, that for these discrete time systems we also say that the input is basically the excitation and the output is basically called as the response. Now, if the input is excited or the system is excited by an impulse function, suppose you give one impulse function, impulse excitation to the system, the output is called impulse response. The corresponding output is called impulse response. That means the response of the system to one input which is impulse. So, that is nothing but impulse response. So, what is the importance of convolution sum now? Convolution sum gives you output from any system if the system's input is known, which is obvious because in order to get output you need the input, and impulse response of the system is known. That means impulse response is the very basic property of the system. That means that to an impulse, what is the response of a system? That is impulse response. So, it is the very basic property of any system. If that property of a system is known along with its input, you can predict the output or calculate the output. So, that is the importance or physical significance of convolution sum. Now, let us come down to this, what is convolution sum and mathematical expression of that. So, yn, output of any given system, is given by yn, which is equal to transformation applied to x of n. X of n is the input, and by now we know that xn can be represented as summation k minus infinity to infinity x of k del of n minus k. Now, from this Now, if the system is linear, we have also discussed that we generally take or design LTI systems, that means linear and time invariant systems. So, linear, if we consider the system to be linear, then this summation of xk gives you a finite value, and that finite value from the principle of homogeneity we can take it out. Say we can write this k minus infinity to infinity x of k transfer function applied to del of n minus k if the system is linear. If the system is linear, we can write from this step to this step, because this part is a constant. Now, in the next step, if we consider the system to be time invariant, we can write that it is equal to summation k minus infinity to infinity x of k h of n minus k, because we have discussed that if the input to a system is del n, the output we say it is hn. Del n means it is impulse, and this hn is known as the impulse response that we were discussing just a few minutes back, that if input to a system is impulse function, output is called impulse response, and that is represented, instead of yn, it is represented by hn. Like for xn input, if the input is xn, we say the output is yn. Likewise, if the input is del n, which that means the impulse, the output is said to be hn or impulse response. Now, here the input is del of n minus k to the system. This is system with transfer function t. Input is, instead of del n, we are taking this as del of n minus k. Now, if input is del n, we know output is hn, and if input is del of n minus k, output will be del h of n minus k if and only if the system is time invariant, then it is not depending on that delay that we have also studied by now. So, from this step we can write this if the system is time invariant. That means, for an LTI system, linear time invariant system, the output yn for a linear time invariant system, the output yn is represented or can be represented by the product of the amplitude and the shifted unit impulse response of the system. That is, this product is called convolution sum. This product is known as convolution sum. That is, output y of n is equal to x of k into h of n minus k, k minus infinity to infinity. That means, if the input is known, input amplitude, if the impulse response is known, you can calculate the output. So, that is the function called convolution or convolution sum, which is very important as far as discrete time systems are concerned. So, by now hopefully you have understood how to represent a signal by shifted unit impulses, then what is convolution sum, and how to represent a system by means of its output and convolution sum. This yn is basically output of the system, which is basically the product of the input. It is not the product, it is the convolution. This symbol is known as convolution sum. This symbol is used for convolution sum. So, output of any system is equal to the convolution sum between its input and the impulse response hn, and this xn convolution hn is actually this summation k minus infinity to infinity x of k h of n minus k. Now, in the next lecture, we will take one example and show you how to solve a convolution sum using real sequences of xn and the impulse response.